chi-square goodness of fit test. The goodness of fit test is used to test hypothesis that an observed frequency, an experimental, fits some claimed distribution. It compares the observed values to an expected or theoretical value to determine if there's an association between two variables. So when we're talking about observed frequency, an experimental, that would be like flipping a coin 10 times. And when you flip a coin 10 times, you're observing what you get. So you might not necessarily get a 50-50 chance of heads or a 50-50 chance of tails when you do the experiment. But the theoretical value, we would expect it to be a 50-50. So the difference between observed is you're doing an experiment, and theoretical, it's a probability of what we would expect to come out. So the statements for the hypotheses for the null is there is no difference between the observed and the expected frequency. And for the alternative, there is a difference between the observed and the expected frequency. So these would be the statements that we would use for the chi-square goodness of fit test. So the characteristics of a chi-square distribution is that it is positively skewed, and it's non-negative, and it's based on a degree of freedom. And when the degree of freedom change, a new distribution is created. So you can see a picture here of what the distribution picture would look like based on the degree of freedom. So the tests for goodness of fit and their notations. The first notation is a capital O. Well, that will represent the observed frequency or counts found by the sample data. And the capital E will represent our expected or theoretical frequency of an outcome. And it's found by assuming that the distribution is as claimed. The K will represent the number of different categories or cells. And the N will represent the number of trials or the total of the observed sample values. And then our lowercase p will represent probability, that a sample value falls within a particular category. So here is the chi-square testing of goodness fit formula to find the test statistic. So this formula incorporates the observed data and the expected data. And this is what you would have to do to calculate your test statistic. Now we will be using the calculator to do this value. Now what we're going to be doing is we're going to be comparing it. And either you can compare this test statistic with which will give us a p-value, and you will compare the p-value to a alpha, a level significance. And if that p-value is less than or equal to your level significance alpha, then you would reject the null. If it's a false statement, then you would fail to reject. Or we'll be finding a critical value, and the critical value will be found in the table, and it's the chi-square distribution table that you would use with the degree of freedom. And the degree of freedom is found by taking the category value and subtracting 1. And the goodness of fit hypothesis test will always be a right tail test. Because it's positive, it's always going to be a right tail test. So if our test statistic is not in the shaded region, we would fail to reject the null hypotheses. If it falls into the shaded region, we would reject the null hypotheses. So you're testing, is your test statistic greater than your critical value? If it's a false statement, we would fail to reject the null hypotheses. So finding the expected frequency. In order to do the test, you're going to need the expected frequency. You're comparing the observed to the expected. So to find the expected, if you're given it is equally likely, To find the expected, you're going to take the number of trials and divide it by the number of categories. So the sum of the frequencies divided by the number of categories will give us our expected frequency. Now, if it's not equally likely, that means that we're given some percentage for each category. And to find the expected frequency, you'll take the sum of the frequencies and multiply it by its expected probability, and you would find the expected frequency. So we're going to find the expected frequency with this example. So the following survey shows the number of employees absent by day of the week at a large manufacturing plant. So we're going to find the expected frequency. So we have a frequency distribution table here. And in order to find the expected frequency, the first thing you're going to need to do is find the total, so that you're going to sum up the frequencies. Once you sum up the frequencies, we have a total from this sample of 445. You're going to take that total and you're going to divide it by the number of categories. And in this case, the number of categories is the days of the week, and it's 5 days. So you'll take your total, divide it by 5, and you'll get the expected frequency for each day would be 89. So for each day, we would expect that the frequency of absences for employees would be 89. This next example is finding expected frequencies when you're giving percentages based on categories. So we have a tax-prepared company randomly selects 300 adults and asks them how they prepare their taxes. The results are shown in the table. So we have our frequencies in the table. The distribution of the tax preparation method is 25% by accountant, 20% by hand, 35% by computer software, 5% by friend or family, and then 15% by tax preparation services. Find the expected frequency. So we are given percentages here. Now, in order to find the expected frequency, I'm going to need the total of frequency. So that's the first thing you're going to do, is find your total. So in this case, when I add up the frequencies, I end up getting 300 as my frequency. And now I'm going to take that 300, and for each category, I'm going to multiply the rate of the category. So for the accountant, it was 25%, by hand was 20, by computer software 35, by friend was 0.5 or 5%, and by tax preparation was 15%. You take that rate and you multiply it by the total, which is 300. So for the accountant, we would expect that it would be 75. For the by hand, 60. For the computer software, 105. For the friend or family, 15. And for the tax preparation services, 45. So this is what we would expect based on what they're telling us the breakdown of percent is. So this is our expected frequency. Pause and try. So this is when we're given percentages, and then you can find your expected frequency. Once you have your total, the total here is 500. And then remember, when you're doing the multiplication of a percent, you always have to convert it to a decimal. So these are the expected frequencies you should have gotten. Pause and try. So in this case, you had to find the total first, and once you found the total, you divided it by the number of categories, and in this case was 4. So you end up with your expected frequency is 12.5 for each category. So when we're finding the critical value by using the chi-square distribution table, it's going to be based on a degree of freedom and a level significance, or alpha. So you're going to look at the alpha value, find the degree of freedom by doing the category -1, and then where it intersects will be your critical value. So you're going to find the critical value by using the table. To find the test statistic, we're going to be using the calculator, and to use the calculator, you're going to have to enter in the data into the list first and make sure you find your expected frequency. So you're going to need the degree of freedom, and you're going to need the expected frequency. Once you have your expected frequency, you want to enter the data into your stat edit list, put the observed in list 1, and the expected frequency in list 2. Once you do that, make sure you have the degree of freedom correct, and then you'll enter and you'll find your test statistic. Now, a key note here is if you have an older calculator, if it's not 84 or above, or 84 plus or above, you will not have this option in your calculator. So you will have to go to the website or the calculator that is online and do the calculation for the test statistic. So the chi-square goodness of fit, for you to use the chi-square goodness of fit test, the following must be true. Of the observed frequency, it must be obtained by a random sample, and each expected frequency must be greater than or equal to 5. So the steps for doing a chi-square goodness of fit test: find the expected frequency and verify that each expected frequency is at least 5, and the observed frequency were from a random sample. And normally that will be stated for you. State your null and your alternative statement. Now remember, the null and the alternative statement, for the null, it would be there's no difference between the observed and expected frequency, and for the alternative, there would be a difference between. Next, you're going to find the critical value by using that table. So again, you could do the p-value, but in our exercises, we will be using the critical value from the table. So to find the critical value from the table, you're going to be given a level of significance, or alpha, and you're going to find your degree of freedom by the category -1. And then you'll look it up on the table, and you'll have your critical value. Then you need to find that test statistic to compare to the critical value. And you're always doing a right tail test. You want to test, is my test statistic greater than my critical value? So you're going to find the test statistic by using the calculator, or you can use the link to the calculator online. So your testing is your test statistic greater than your critical value? If it is a true statement, you're going to reject the null. Otherwise, you're going to fail to reject the null. Always, always right tail. It's always right tail, so you're always testing, is the test statistic greater than your critical value? So if you reject the null, there is a difference between the expected and there is a difference between the observed and the expected frequency. If you fail to reject the null, then there is no difference between the observed and the expected frequency. So we're going to do an example for testing the goodness of fit. And we did this example to find the expected frequency. This is the example where we have a number of employees absent by day of the week for a large manufacturer. And we found that the expected frequency here was 89 for each day. And we found that, again, by doing the total divided by the number of categories. Next, we're going to state the null and the alternative statement. So the null is there is no difference in absent rate by day of the week. And the alternative is the absent rate by day are not equal. Now I'm going to identify alpha, which is given as 0.05, and the degree of freedom. And the degree of freedom is categories -1, and in this case we have 5 categories, Monday through Friday. -1 would equal 4. So now I'm going to go to the degree of freedom on the table and go over to 0.05 alpha, and I'm going to find my critical value. So in this case, my critical value is 9.488. Now we want to find that test statistic. In order to find the test statistic, you're going to have to first enter in the data into your calculators. So go to Stat and Edit. Enter in the observed list into list 1 and the expected list into list 2. Once you have the data entered into the calculator, then you can calculate the test statistic. To calculate the test statistic, you go to Stat, arrow over to Test, and you're going to choose the chi-square goodness of fit test. Observed should have list 1 in it, expected should have list 2, and enter in the degree of freedom, and in this case it's 4. Hit enter and you're going to find your test statistic. So our test statistic here is 60.90. Now I'm testing, is 60.90 greater than our critical value? And in this case, it's a true statement. 60.90 is greater than 9.488. Because it's a true statement, we're going to reject the null hypotheses. Because we're rejecting the null, we can state that the absent rate are not the same for each day of the week, or there's a difference between the absent rate based on the day of the week. Pause and try. So the first thing you had to do here is find your expected frequency, and it was based on percentages. So we have our expected frequency. Then you're going to find the statements, and it's based on distribution has not changed or the distribution has changed. You find your critical value and your test statistic and you compare. Because our test statistic 13.095 is greater than our critical value 7.815, we reject the null hypotheses. And because you're rejecting the null, we can state the distribution regarding marital status in Philadelphia is different from the rest of the United States. So now we're going to work with contingency tables. And contingency tables have rows and columns. And it shows the observed frequency for two variables. The observed frequency are arranged in rows and columns. So rows will be denoted with R and columns will be denoted as C. The intersection of the rows and columns is called a cell. So in this case, the chi-square test for independence. So it's working with the chi-square test. We're going to have a hypothesis. We're going to be comparing our observed frequency in the table to a expected frequency of the table. And then the statement for the null hypotheses is that the two categorical variables are independent or the two categorical variables are dependent. So when we're testing for independence, whether the two categorical values are independent or they are dependent. Another way that we might see the statement would be that there's no relationships between the categories or there is a relationship between the categories. So it's either independent or dependent, no relationship, or there is a relationship. The test statistic formula is the same as we did for a frequency distribution table, but now we're going to have a contingency table. So the O represents our observed, the expected, or the E represents our expected. We would find the p-value using the calculator, and we're going to find our critical value the same way. When we find the critical value, though, our degree of freedom is going to be based on our row minus 1 times the column minus 1. So it's important that the degree of freedom is calculated correctly to find that critical value. And this will also be a right tail test. So if our test statistic does not fall in the shaded region, we would fail to reject the null. If it falls in the shaded region, then we reject the null. So finding the expected frequency. When you're finding the expected frequency in a cell, you have to take the row total times the column total and divide it by the grand total. So the table given represents the observed count table, and we're going to need to create an expected count table. So we're going to do an example of how to find the expected frequency for a contingency table. So in this case, we have an example of how the smoking habits of students related to their parents' smoking. Here are the data from a survey of students in 8 Arizona high schools. Find the expected frequency. So the formula again is taking the row total multiplied by the column total divided by the grand total. And you have to do that for each cell. So we're going to have to first, in order to start, you need the totals for the rows and columns. So you want to add up the columns and the rows and get the totals. So you see the totals here, and then the grand total would be 5,375. Now that you have all the totals, you can find the expected frequency. So we're going to start by finding the expected frequency for the first cell. And the first cell has that 400 in it, and I want to find the expected frequency. To do this, I need to take the row total and multiply it to the column total and divide it by the grand total. So in this case, we end up with to be 332.49. And I'm going to do that for each cell. So I go to the next cell, and I need the total for that cell in the observed frequency, and I'm going to take the total row times the total column divided by the grand total, and I'm going to get that expected frequency. I'm going to do it for the next cell, and again, you have to make sure that you're using the correct totals when you're doing the expected frequency. So I'm getting the total from that row times the total from that column divided by the grand total. And you're going to keep on doing that. You're going to repeat until the entire expected frequency table is filled in. So that's how you find the expected frequency for a contingency table. Pause and try. So first you needed to find the totals in order to find the expected frequencies and the grand total. Now that you have the totals for the rows and columns, you can find the expected frequencies as your expected frequencies. So to find the critical value when we're doing the hypothesis testing for the chi-square, you're going to find it the same way you did for the frequency distribution table. You're going to look for alpha, you're going to find that degree of freedom, but the degree of freedom will be based on the number of rows and columns. You're going to take the number of rows minus 1 times the number of columns minus 1, and you'll find your degree of freedom. Then you'll find the critical value where they intersect. To find the test statistic for the chi-square goodness of fit when we're working with contingency tables, first you're going to need to find the expected values. Now we're going to be using the calculators to do the expected values versus doing it manually. And in order to find the expected values in the calculator, we're going to need to use our Matric function. So you see here under the note, we're going to find it by either, if you have an older calculator, it has a matric key that you'll use. If you have a newer calculator, you're going to have to do the second button and go to where that x-1 is and the word matrix above it. Once you get to that function, you're going to arrow over to edit. And then we're going to choose the first matrix name, which is A. And then when you do that, you want to enter in the number of rows and the number of columns. And then you'll enter in the data. Once you have that data entered in, you can quit. And then notice in the function to find the test statistic for the observed, it has a matrix symbol A, and for the expected, it has a matrix symbol B. So when you go to this function, it will calculate the expected value for us. So the chi-square independence test, it has to have the following, which is the observed frequency must be obtained by a random sample, and that the expectant frequencies must be greater than or equal to 5. The process you're going to take for the chi-square goodness of fit test for a contingency table is you're going to verify that it meets the conditions, and then you're going to state your null and your alternative statement. And we're testing for independence or relationship or no relationship. So to find the critical value, you're going to need that degree of freedom and the level significance or alpha, and you're going to look it up on the table. And then we're going to find our test statistic. Once we have that, we're going to compare. Is our test statistic greater than our critical value? If this is a true statement, you'll reject the null. Otherwise, you fail to reject. So again, it's always going to be a right tail test. If you reject the null, then we have independence of categories. If we fail to reject, then the categories are dependent. So we're going to do an example here, the chi-square independence test. So we have a health club manager wants to determine whether the number of days per week that college students exercise is related to gender. A random sample of 275 college students is selected, and the results are shown in this table. At a level significance of 0.05 or alpha equals 0.05, is there enough evidence to conclude that the number of days a student exercises per week is related to gender? So the first thing I'm going to do is state the null and the alternative. So the null is the number of days exercised per week is independent of gender. Or the alternative, which is the number of days exercised per week, is dependent on gender. The next thing we want to do is find that critical value. To find the critical value, we need alpha, and our alpha in this case is that 0.05, and we need our degree of freedom. So the number of rows in this case will be 2, and the number of columns is 4. So 2 minus 1 times 4 minus 1 will equal 3. So our degree of freedom is 3, our level significance is 0.05, and we find our critical value is 7.815. So now we're going to find that test statistic. To find the test statistic, the first thing we want to do is enter in the data into our matrix function. So we're going to enter in the table no totals, only the data, no totals into the calculator. To do this, if you have a newer calculator, you're going to go to second, the x minus 1, which has the matrix function above it. If you have the older calculator, you have that matrix button. What you need to do is you need to arrow over to edit. And in edit, you should see the number 1 is A, and you're going to enter in the number of rows, and in this case is 2. And the number of columns is 4. Then it's going to have a blank table that you're going to fill in this data. So you're going to type in the table values, and you're going to start by typing in the first row, which is that 40, 53, 26, and 6. And then you're going to type in the second row, the 34, 68, 37, and 11. Now in order to get the number of rows and columns, you have to make sure that the numbers are correct at the very top, that you have 2 for the first option and 4 for the second. The 2 times 4 means that you have 2 rows times 4 columns. Now that you have the data entered in, you're going to have to quit to go to the main screen. To go to the main screen, you're going to do second mode, and above mode you see the word quit. So that will get you to the main screen. Now you're going to go to your stat button and arrow over to test. Choose the option that has the chi-square symbol test. It's just the chi-square symbol test. In most calculators it's the value C, but make sure you're in the right option. Then you're going to have this screen where it already has the observed with your matrix A in there, and the expected will be calculated for us. So the observed should have A in it, and the expected should have B in it. If it is not entered in there, to find those options, you will need to go to that matrix menu again, and you're going to arrow over to name and then pull that matrix name in there. For most calculators, it will already be in there as A and B, but if it's not, that's how you get it in there. Once you have the correct matrix names in there, then you're going to calculate. And we calculate it, and we end up with our test statistic and our p-value. So our test statistic here is 3.493, and we're testing, is that greater than our critical value? Is our test statistic greater? And in this case, it is not. 3.493 is not greater than 7.815. It's a false statement, and because it's a false statement, we fail to reject the null. We fail to reject the null. Therefore, there is not enough evidence that the number of days of exercise per week are related to gender. They are independent of each other. Pause and try. So your statement here is CEO ages are independent of company size, or they are dependent of company size. We got a critical value of 13.277 and a test statistic of 77.887. When you do the comparison, it is a true statement, and because it's a true statement, we can reject the null, and if they reject the null, then we can state that there is enough evidence to conclude that the CEO's ages are dependent on company size.